So our next subject is digital modulation techniques. We are going to do the introduction in this lecture and proceed all the way to ASK. So to start with, we just mentioned that there's a number of learning objectives that we should have in mind, or at the end of the lecture or at the end of the topic we should have. That one, we should be able to explain the difference between the bit rate and baud rate, describe and compare ASK, FSK, and PSK modulation techniques. So that is at the end of probably lecture 7. That is when we anticipate to have finished with discussing all the digital modulation techniques. So we are going to be discussing QPSK, OQPSK, which is also called offset QPSK, quadrature amplitude modulation, that is QAM, and Gaussian modulation, GMSK. GMSK is for Gaussian minimum shift key. So those are a bit more advanced digital modulation techniques, the way slightly that are more practical in today's world than the pure ASK, FSK, and PSK, and therefore we are going to be looking at them as well. The other objective is to understand the carrier synchronization for coherent detection, and I think I mentioned about synchronizing the clock of the carrier signal for us to achieve coherent detection. And last but not least is to understand or perform some performance analysis for different digital modulation techniques. So as an introduction, we say now that digital modulation is the transmission of digitally modulated analog carrier signals in bandpass communication system. So the idea is that we are not using the analog modulation here, but the key point to remember is that we are dealing with an analog carrier. So the message MT is digital, but the carrier, sometimes we call as CT, is analog. The other point to remember is that for the analog modulation, M of T and C of T are both analog. So the difference here clearly stands out that for the digital or the bandpass modulation or the digital modulation technique, we use digital message and still the analog carrier. The other key point to mention is that we may perform the modulation in which we may use the message to modify the amplitude, the frequency, or the phase of the carrier. So that is where we normally derive the difference between the three primary modulation techniques. So when you modify the amplitude, you obtain ASK. When you obtain the frequency, you obtain the FSK. And finally, when you modulate or when you vary the phase, you end up with PSK. And of course, that is what we are mentioning here, that we have FSK, ASK, and PSK. And therefore, the digital modulation system offers several outstanding advantages over the traditional modulation systems, such that it is easier and provides faster signal processing. These are some of the advantages that we should mention. That one, it's easier to perform signal processing, of course, even faster. So if you are asked some of the advantages of digital modulation scheme, there are some of the items that that should be on your fingertips. The other thing is that it provides greater noise immunity and robustness to channel impairment. So clearly that when the channel introduces errors or noise, then we are saying that the digital moderation scheme will be more resilient, and therefore still we are going to be able to receive the intended message at the receiver or at the sync end. So, but PSK has the potential of transmitting digital information with the lowest possible of errors. So we actually observe that this one is way advanced than both ASK and FSK. So we'll actually observe that it is the PSK that has even more advanced uh, versions way beyond what ASK can offer. So we are also saying that QAM and GMSK are bandwidth efficient moderation techniques, and we will see them as the chapter progresses. So, so this chapter represents a detailed discussion of all these digital modulation techniques, including their characteristics or their spectral characteristics, their noise performance, and advantages and disadvantages of each. And we are going to be doing some comparative study on how they are applicable in different applications. We now try to differentiate between the types of digital moderation schemes, and the first one is that is the one that we can say we have definition of digital moderation scheme and binary modulation. These two terms sometimes may appear as though they mean the same, but there is a slight difference that comes as follows. That one, digital modulation involves the process of varying. My note is missing the word varying. The digital modulation involves the process of varying the amplitude, frequency, and phase, as I have mentioned, of an analog carrier. Never forget that you're talking about analog carrier as a function of two or more finite discrete values. So when you say binary, we actually saying on the contrary, they are actually, or they are only two discrete values. So when it is two, it becomes binary. When it is more than two, remains digital modulation, because for the binary modulation, we are saying is the same process, but we only have two finite discrete states, 0 or 1. So that is the unique difference. So when we are talking about QPSK or 8PSK or QAM, this stops being binary and remains being digital. Whereas when you're talking about BPSK, or BESK or BFSK, then this is the ones that can be categorized as falling under the category of binary modulation. So without going into too much details, we want to just highlight how each of them is achieved. That is ASK, FSK, and PSK. We say that we consider that our analog carrier may be represented by as an equation of this form, where this is the amplitude, this is the frequency, and this is the phase. And therefore, when we want to vary, when we vary the amplitude, we achieve ASK. When we vary the FC, we achieve the FSK. And when we vary the phase, we achieve the ASK. So that is purely what this statement says. And for the sake of illustration, I just jump to this diagram or to this figure that purely illustrates what we mean when we say vary. Consider your digital message to be a series of ones and zeros, which can be represented by a unipolar non-return to zero line code that is of this form. And now consider that you have a carrier of frequency f as represented by this diagram, or this series of pulses, of sine pulses. So when we say that we want to vary the amplitude of this carrier, with respect to the incoming binary sequence of ones and zeros, what we are simply saying is that for the period when we have symbol 1, then we are going to maintain the amplitude at maximum value of the one we had called VC. And when the sequence changes from 1 to 0, we're saying that we vary the amplitude. Remember, the amplitude is what is varying from 0 point to maximum of VC. So when we set this amplitude depending on what value of incoming binary sequence we have, then we achieve the binary sequence, or rather the ASK, and therefore this is the amplitude. So, but if you are varying the frequency, which I will show you shortly, then we say that it qualifies to be called the FSK. So for the record, that introduces the three. So I feel it's sufficient just showing what I have said. We will go into how we achieve FSK and PSK shortly. So we now just notice this important point that amplitude shift keying, FSK and PSK are collectively known as the digital modulation schemes, and there are a number of them which fall under the category of binary or M-array modulation schemes. When we say M, we normally take it to be M is technically more than 2, but by definition, it says anything that is M, which might be 2 and above. So we are saying that binary will be having BFSK, and when you see B, you know that it talks about binary. But then M-array says that they are of higher order modulation schemes. And there's something very significant that we should also understand regarding how the objectives or the design objectives of the digital modulation schemes. And we normally say that we have some desirable features we normally seek to attain when we are designing a modulation scheme, because some modulation schemes have advantages over the others, and for that reason we might opt for one modulation scheme over the other. So what our generally the design objective is that when we are designing, we normally try to maximize data rate such that you achieve the highest possible data rate, because clearly your incoming bit of bit sequence of ones and zeros, you might want to be able to process probably 1,000 of them in 1 minute or in 1 second, and therefore the higher the data rate, the better. The other objective is we normally say we try to minimize the transmitted power. We maximize. Of course, you want to have to set minimum power, because power is expensive. Therefore, you definitely want to use little power to achieve the same objective. The other objective is to have maximum utilization of channel bandwidth. When you talk about a channel, you're talking about a channel that might be a pipe. If you talk about in layman language, it is like you're talking about a pipe, and therefore you want to transmit people in this pipe, and you want to transmit as many of them as possible. So we are clearly saying that channel is band limited, or the bandwidth of the channel is limited. You cannot not expand this channel indefinitely. So what you need is to make sure that if you can be able to squeeze as many people as possible through this channel, the better. So we are saying that we try to maximize the utilization of the channel. And of course, we want to have as many people die along this channel as possible. So you don't want some of them being crushed by others as they are being ferried along the channel. So when you see this kind of a person or this analogy, this means that there are some errors that are arising in the channel, and therefore if you have so many of errors, then that means that it is not good. So we want to minimize the probability of error through our system. And the other objective is to normally to maximize resistance to interference. So we are saying that as these guys get or traverse, when I say these guys, I actually mean data. When they traverse, we don't want them to be have interference by others. I don't think there is likely. Okay, yeah, probably we should have some probably there are loopholes here, whereby there are some other people who are not supposed to go through the channel in terms of interference. They are getting into the channel and therefore causing the people we are receiving or the guys we are receiving on this end to be confused. Like we are expecting only students in the uniform, so you are getting students here. But here, at the end of the day, we get crooks plus the students. So that would be the analogy we would give, that we only want the students on the receiving end because we sent the students. So I'm just using that for the sake of illustration. And therefore, when you get crooks together, some guys who are pretending to be students but they are not, then we are saying that this channel is experiencing interference or losses and errors, and therefore it is not serving its purpose. So that is one of the design objectives. And lastly, in terms of the design objectives, is that we want to achieve minimum system complexity. Sometimes some of the modulation schemes have very good objectives. They have very high data rates, but that comes at the cost of complexity. Therefore, sometimes we may not have the capacity to achieve the highly complex system. Therefore, we will normally try to achieve to seek minimum system complexity for our purposes. So these are the design objectives that when we are designing or when we are selecting or choosing a modulation scheme, we normally seek to fulfill. We're still at the introduction before we jump to the ASK. And to summarize, we should also be able to differentiate between bit rate and baud rate. We simply say that bit rate refers to the rate of change of binary data. So we only have two symbols, so that is 1 or 0, and therefore the rate of change for those symbols is the one that we consider to be the bit rate. So it's the number of bits per second, and therefore you see that we normally express the quantity in terms of bits per second. And the other definition that for that suffices to introduce the measure of data flow is the concept of baud rate, and we say that baud rate refers to the symbol rate. Actually, it is actually the number of symbols that can pass through your channel or through your scheme per second. So if you have a symbol and we are saying that a symbol may be represented by, say, more than 1 bit, say something like that, this might represent 1 symbol. So the more they have the symbols, the more the symbols that are flowing per second, the higher the baud rate. But clearly you can see that the baud rate is normally lower than uh, the the bit rate, simply because it is of higher order, of higher magnitude. It's like you're asking yourself, how many ones do you have in 100? So clearly we have only 100, but if you talk about ones, you are talking about 100 ones. So this would represent the bit rate, whereas the ones or the 100 would represent the baud rate. So I've just given the example that we done in the elementary school or in primary school, where you are normally asked which one is high, which one is bigger, 100 or ones, or hundreds or ones. You definitely choose the 100, but it has lower magnitude and vice versa. So that services for the introduction of about bit rate and baud rate. And we also observe that the baud rate is a very common phrase that we need to get used to. It is also has the same meaning as the transmission rate, symbol rate, or the modulation rate. And therefore, um, we have to mention that. The other thing that we should, as we conclude this subsection, we should consider is there are some limiting factors of transmitting digital data over analog channel. And we say now, we say that, so this is actually a question that we are asking ourselves: what is the limiting factor of transmitting digital data over analog channel? And we actually observe that all types of communication channels, such as telephone lines, and you are conversant with this, the optical fiber. When you hear about Jamii fiber or Safaricom fiber, where they are talking about sending information in a fiber or it's a form of light, and therefore the fiber cable that receives light at this end and is received on this other end is the one that is called optical fiber. Microwave is what we normally use to transmit data from one base station, say from your phone to the BTS or to the base transceiver station. This the frequencies that we use are the ones, or the concept that we use here is the one that's called microwave. Satellite is the one that allows you to transmit between the ground or the earth, sends to some satellite in way beyond atmosphere, probably in the troposphere here. So you are transmitting from this end. You normally transmit to this satellite receiver, and then someone on the ground receives a signal from the satellite. So this is the one that we refer to as the satellite links. And we are saying that all these, and I think the best example for this one is the DSTV. Some of you might be very conversant with the concept of DSTV. They use it satellite, so to transmit their signals or for video or for streaming. So that we say that all these have limitation on the bandwidth. So how much spectral quantity can one channel occupy? We say that it is not unlimited. It is not infinite. So we are saying that the limiting factor for transmitting digital data over analog channel is purely the bandwidth. And therefore, we are saying that we normally require to transmit within a finite bandwidth, because almost all of our channels that we have will not accommodate infinite bandwidth.